All right, so what makes this one tricky is that it's a velocity versus time graph. And the ones you've done before this were position time graphs. So you get into that frame of mind where you're thinking a position versus time graph works like this, and then you have to shift gears. Okay, so the first part of this is we want to calculate the acceleration between 12 seconds and 14 seconds. All right, so an acceleration is a change in velocity. All right, so an acceleration is any change in velocity of an object, okay? And obviously between 12 and 14 seconds, there is a change in velocity going on, all right? So if I want to calculate the change in velocity, essentially, I want to calculate what about this line? Its slope, right? That will tell me how quickly the velocity is changing, right? Because it'll be the change in velocity divided by the time, right? So I'll get meters per second per second. We had talked about that last week a little bit. Is that ringing a bell a little bit? Okay, so what I'm going to do then is calculate the slope of that line, all right? Essentially, that's using this formula, which we may talk about today, definitely tomorrow, okay? Our acceleration formula. Acceleration is the change in velocity, final velocity minus initial velocity, over time, which happens to be on this graph, kind of like that. Obviously not for this section, but it's sort of like that, right? It's the slope of the line. Okay, so for this one, okay, we're just going to use the final velocity, which is at 14 seconds, okay, is -6. Okay, and then I'm going to subtract the initial velocity, which was +2, and then I'm going to divide that by the time. Between 12 and 14 seconds is 2 seconds. All right, so 6 minus 2, or -6 minus 2, sorry, is -8. Okay, divide that by 2 seconds. Okay, this is meters per second. This is seconds, so I'm going to get -4 meters per second squared. Okay, or meters per second. All right, is that ringing a bell? Nick? Okay, so it's seconds per second because I'm calculating the change in velocity, which is in meters per second. And then I'm telling them how fast I'm changing that velocity. So I'm going this many meters per second faster every second. So I'm changing by this many meters per second. Yeah? No, I did not find the area. That's for displacement, right? Because when we find the area, what we're doing is taking average velocity and multiplying by time, right? Base times height, right? And then that gives us our displacement. Yeah. If it's a triangle, right? That's why I put average here. If it's unchanging, the average is just whatever the number is. If it's a triangle, then it's base over or height over 2. There is a formula sheet. You do not have to print it off because I will. Once I get you guys going on one more of these, that's my job for today, is to print your formula sheets, because I've been meaning to do it for a week. I keep forgetting. Okay, so does that part make sense there? Calculating the acceleration? Okay, so essentially it's the slope of the line using this formula, which we'll talk more about today or tomorrow. All right, the total displacement over the whole trip. This takes a really long time, okay? Doing question B takes a really long time because we have a whole bunch of different shapes, because we have a whole bunch of different velocities and changes in velocity on this graph, right? So what we want to do first is kind of identify all those shapes, okay? In this part, what's the displacement? 0, because it's not moving there, okay? How do I know it's not moving there? Right, the velocity is 0 meters per second for the first 2 seconds. It's impossible to go anywhere that way. All right, then it's going to accelerate from 0 to -3, okay? And then it's going to accelerate from -3 to +2, but I'm going to make that 2 different shapes. Okay, so I'm going to have this triangle here, okay? This triangle here, this little one here, then I'm going to have a rectangle here. Why do I want to use this rectangle? Right, it's traveling at a constant speed during that time, and that's kind of the easier ones to do, okay? Because it's just base times height. It's velocity times time, and I get the distance traveled. Okay, then I've got this really skinny triangle here, and then I've got this triangle here. Okay, and then I would say probably like this. I would go like this. So I have a triangle and then a rectangle under it. Okay, what I'm doing with these shapes is I'm just identifying different patterns in the graph. Sometimes it's accelerating, and sometimes it's traveling at a constant velocity. And I want to separate those times, okay? Because I calculate how far it goes during those sections differently, right? So I want to separate them all. All right, if I want to calculate how far, sorry, what the displacement is during this first triangle here, okay? I know that this first triangle takes 1, 2, 3 seconds. All right, so the time is going to be 3 seconds, and it changes its velocity from 0 to -3. All right, so we said we want to take the average velocity and multiply by time. Since the velocity is changing from 0 to 3, what's the average? 1.5. Okay, again, that's height over 2 times the base. Average velocity times time. Okay. So we're calculating the area, because calculating the area really just uses that formula. Okay, so for this first graph, then that's going to be 1.5 times 3. Okay, and 1.5 times 3 should be 4.5. Yeah? Someone might want to double check my math. Okay, so during that triangle, it travels 4.5 meters. It's velocity. It's negative. Okay, aren't I going backwards here? Right? Isn't my area negative? Okay. There's lots. This is the thing about physics. It's detail oriented. So you really have to be on the ball about your details. Okay. All right. Then we have this little tiny triangle that's 1 second on the base and 3 seconds tall. Or sorry, 3 meters per second tall. All right. So I'm going to do the same thing. Okay. I'm going to go 3 divided by 2, so height over 2, and then multiply that. So this is just going to be 1.5. All right. And it's still negative because it's still below the x-axis.
What is the displacement from 0 because we're starting at
No, because this is a velocity versus time graph. If it was a position versus time graph, you'd be right. Okay, but in this case, this is showing my different velocities. I probably do end up having a displacement that's not 0 because it appears to me I go backwards a lot more than I go forwards. Right? Like the graph spends a lot more time in the negatives than it does in the positives, right? Okay, so for right here, okay, I've got this little tiny sliver of a triangle that's 1 second on the base and 2 seconds high. So it's going to have an area of 2 times 1 over 2, which is 1, positive 1 meter. Okay, then I've got this rectangle that's 1, 2, 3, 4, 5 seconds long and 2 tall, so that's going to be 5 times 2. Okay, so 10 meters tall, or 10 meters, 10 meters in area. Then I have this little tiny triangle that's only a half a second on the base. Okay, because you can see this is 1 second and that's another second, so it's only half a second on the base. Okay, it's 2 times 1/2, which is 1, divided by 2, which is 1/2. And it's positive. All right, then I've got these triangles down here. Okay, so this triangle, this tall one, okay, this one right here, is 1.5 seconds on the base, and it is 6 seconds or 6 meters per second tall. So 6 times 1.5 is 9, divided by 2 is 4.5. Yeah, it doesn't matter what order. It'll come out the same, right? Okay. Because otherwise, if I just went 6 divided by 2, I'd get 3 times 1.5, I'd get still 4.5. Either way it'll work, right? Okay, and that's going to be negative. Then I have this triangle here. Okay, this triangle only goes from -2 to -6, so it's got a height of -4. Okay, and it's 2 seconds long, so -4 times 2 is 8, over 2 is negative 4 meters. Okay, then I have this rectangle here that's 1, 2, 3, 4 seconds and negative 2 meters per second high. So this is going to be negative 8 meters. And then I have this triangle here that's negative 2 high and 1 long. So negative 2 times 1 is negative 2 divided by 2. All right, so now I've got all the areas calculated.
How did you know that how did you know that on the one that's like on the 0.5?
Yeah.
How do you know it's not 0.75?
If I blow that graph up, it'll be a little bit clearer, but it goes directly between the two. So there's a little bit of estimation there. On a test, I wouldn't make it where you would have to estimate. It would clearly go through numbers, yeah. All right, what's my next step now that I got all those areas? Add them all together, making sure I keep the signs, okay, the negatives and positives, because I'm looking for a vector quantity. Okay, so then we'll go negative, well, not point, negative 4.5 plus negative 1.5 plus 1 plus 10 plus 0.5 plus negative 4.5 plus negative 4 plus negative 8 plus negative 1. All right. So the total displacement is negative 12 meters, right? We did spend quite a bit more time going backwards according to this graph than we did going forward. So it makes sense that we should have a negative displacement. Jake, question? Because the areas come out to meters. The sides are in meters per second or in seconds. Right? Like when I calculated these areas, okay, I was taking velocities and multiplying by time, which gives me meters. If I just take one of the sides, I'm going to have meters per second. I was asked to find displacement. Adding velocities together doesn't give me displacement. No, if I'm actually calculating the area of a shape that's meters by meters, it would be meters squared. But these shapes are meters per second by seconds. Okay, like the heights of all these triangles are in meters per second, not meters. Okay, and the bases of all of them are in seconds. So I'm finding the area, but I'm not really looking for area per se. I'm looking for what the area represents. Yeah. No, it's 4 long by 2 high. No, it's this whole thing. I didn't remember this triangle here I cut off, right? This triangle only went to here, not all the way to the bottom. Yeah? It's easier that way. It's less shapes. If I make this triangle go all the way to there, okay, then I've got a triangle and another rectangle and a little triangle. That's a mess, right? This limits the number of shapes. Does that make more sense? Okay. All right. Would I give you one like that on an exam where time's a factor? Wow. I'm hurt. No, I would not give you one like that. I would give you one that looked like this maybe. Like 1, 2, 3. Okay. Can that tell me whether you know how to do it? Does it take like 1/4 as long as this one? Okay. That's what I'm looking for on a test. Okay. This just helps you practice. That's why it's on a worksheet. Okay. When I'm evaluating whether you can do it or not, I don't need to know how quickly you can do it, just whether you can do it. All right. So I wouldn't give you one that takes, I mean, that took me, who knows how to do this and has done this particular question more times than I care to mention. It still took me, what, 8, 9 minutes? Right? Now, granted, I was explaining it. If I was just doing it on paper, it wouldn't take that long, but it takes a while because it's repetitive. Okay. Does everyone kind of get what we did there? Find all the shapes, we get the areas of the shapes, we add the areas up. Okay. Because when we find the area, we're really just taking average velocity times time. Okay. All right, so we found the total displacement. That was part B. Part C said, what's the average velocity over the whole trip? Okay, did I just find one of the things I need for that? Yeah, okay, I just found the displacement. Do I know how long the whole trip took? Yeah, I can read that off the graph, right? The whole trip took 20 seconds. So I take my negative 12 meters, divide by 20 seconds, and I've got my, my velocity over the whole trip, which should be negative 0.6 meters per second. Okay, just V equals D over T, right? Okay, and then the average acceleration between 14 and 20 seconds. All right, so I'm going to take this stuff off of here now. Okay, so between 14 and 20. That's not one solid line, is it? No, it's not. But can I still use this formula? Yeah, I still have a final velocity, which on this is 0. I still have an initial velocity, -6. And I know that between 14 and 20 seconds is 6 seconds. All right, so I just go 0 minus -6 over 6, right? And I'm going to get positive 1 meter per second or meter per second squared. All right? Everybody follow there. All right. We'll probably get to where we manipulate that formula tomorrow. Okay, but that's the acceleration formula that you will use in Science 10. It's the only one. In Physics 20, there are 5. Okay, in Science 10, there's only one. How many of you are looking at that going right now going, oh, I can't use a triangle. You can't use a triangle. I told you so. Okay, no more triangles. Okay, it's got a plus or a minus in it now. That triangle is out the window. Okay, so you might have been getting away with it until now. No, not that I know of. Okay, how many people are to question number 5? Okay, try question number 5 right now. It's up here on the board, so you don't have to look it up on your phone. Okay, it's another velocity versus time graph, but this is more like what I would give you on a test because it has less sections. Okay, it has way less sections than the last one. Imagine that these are actually not curved, that they're just rigid, so they're like a triangle. Okay, so forget that they're a curve. Okay, this part here goes to right there, and this part here goes to right here. Okay, so just imagine it's a triangle. It's not curved. I don't know why they curved that. But. All right, I'll give you a couple minutes on that one. And I'm going to photocopy your formula sheets. Okay, so for part A, okay, listen in here, guys. For part A, okay, we want to find the total displacement over the whole trip. Okay, if I just look critically at this, do I need to do any math? No, because the shape above and below the line are identical. Okay, so I don't really need to go any further than that if I just kind of looked at this and said, all right, here's a rectangle and here's a rectangle. Those are the same, and these two triangles are the same. So if I calculated the areas of these shapes, they would do what to each other? They'd cancel each other out because one's positive, one's negative. I could go through all the math and do it, but I don't really need to. Okay, I can just see that visually above and below the line are going to cancel each other. All right. Now, for part B, okay, so if I gave you a question like this on a test and I add that question, it would be out of 1 mark. Okay, because it actually doesn't require, and I wouldn't expect that you would do any work. I would expect that you'd be able to look at that and just know, oh, well, those cancel at 0. Okay? No, but what I find is when people do work, they're doing the wrong work. Okay? If a question is out of 1 mark, how much work is there? None. There isn't any work. It's a recognition answer only. Okay, so just know that, okay, because it comes up sometimes on a test. There's a question, it's only out of 1 mark. Okay, I see people sometimes write down 5 or 6 marks worth of work that's all wrong, proving something that's not right. Okay, it's just because they haven't understood the question. If something's out of 1 mark, you don't need to do any work. Okay? The answer is there in front of you. You just have to discover it. All right, for part B, okay, find the average acceleration between 5 seconds, so that's right here, and 15 seconds, right here. All right, so acceleration is the change in velocity, Vf minus Vi, over the change in time. Okay, so Vf is +8, Vi is -8, and between 5 and 15 seconds, there are 10 seconds. Okay, so Positive 8 minus negative 8 is positive 16. Divided by 10 should give me positive 1.6 meters per second squared. I don't cancel anything. I don't cancel anything. I'm dividing meters per second by seconds. I have meters per second over seconds. No, when you subtract, it's a difference. The units don't change. Only when you multiply or divide do units change. When I'm adding or subtracting, like if I have apples plus apples, I don't get 2x apples or apples squared when I'm adding them, right? I just have apples. Follow me there? But if I divide apples by crates, that's apples per crate. Yeah? You follow me there? I don't know if that was a good analogy or not, but it just kind of came off the top of my head. Oh, okay. All right, but you follow the unit analysis there? Okay. And then for part C, it wants to know the average speed over the whole trip. Well, what two things do I need for that? Just total distance and total time. Well, total time's easy. We can read that off the graph. It's 20 seconds. Okay. What I need to know now is I do actually have to calculate the areas of these shapes. Well, actually, I only have to calculate the areas of these shapes because those shapes are the same, right? I can save myself some work. All right, so this one here is negative 8 times 5, so this is 40, and this is half of that. Okay, so I've got 120, okay, as my total distance traveled. 60 on the bottom, 60 on the top. Remember, distance is scalar. It doesn't care which direction we go. Okay, so I'm going to take my total distance divided by my total time. So, sorry, there should be no line there. That equals speed. 120 over 20 is 6 meters per second. Oh, sorry, I didn't put units on that. Okay. All right, and guys, that's an exam question. Okay, like I wouldn't make it any more difficult than that. That tells me you know what to do with a velocity versus time graph. That asks you to do basically everything that I've taught you to do with a velocity versus time graph, right? Okay, that one's going to take a lot longer because it's got a lot of what? Lots of shapes. Okay, but we want to try and minimize the number of shapes, right? So could I make like a big rectangle like that? Yeah, that limits the number of shapes, right? If you any time you can do that, try to. Now, the way this question goes, it doesn't always mean the whole thing, right? It might ask you between A and F. Well, that's only to here, right? So I'd have to cut part of that off or whatever. But always try and limit the number of shapes you actually have to draw.
So if you find an area of that big rectangle there, are you finding between D and E?
No, if I'm trying to find the displacement between D and E, is that what it asked for first? Oh, okay. If I'm trying to find the displacement between D and E, that's it, that rectangle. Right, because it travels at a constant velocity for that time period. Okay? If it asked between A and C, then I would have a triangle and a rectangle.
But if it's asking between D and G, you just make that big rectangle and you also find everything else.
Well, between B and G, I would have, yes, this rectangle here, for sure. But this also happened between B and G, so I also have to take all of it into account. Yeah, but that would be the minimal number of shapes to do it with, right? Because some people would say, well, why don't you go all the way to the bottom with this one? I'm like, well, that's more shapes. Right? Then I'm splitting this rectangle up suddenly into a bunch of other shapes. Why not just go with one big rectangle and kind of go from there? Well, only if it wanted to go to H, yes. But we were just asking between B and G. This is what we would have to do. You're right. If it was for the whole trip, yes, I'd make that rectangle all the way over. Okay. All right. Let's have you work on 6 for a little while. Okay. We'll go over it in a few minutes. Sorry, part A wants us to calculate the acceleration between A and B. All right, well, acceleration, like we said, is the change in velocity over time. All right? So VF is 20, VI was 0, and that took 2 seconds. So 20 over 2 is 10 meters per second squared, and that should be positive. Acceleration is a vector quantity, okay? That shows that the velocity was increasing, okay? For part B, it wants to know the displacement between A and E. All right, so between A and E would just mean that I would cut off right there instead of going all the way, okay? So to calculate that, all right, I've got this triangle here that's going to be base times height over 2, so 20 times 2 is 40, over 2 is 20. I'll have this big rectangle here that goes from 2 to 8, so it's 6 on the base, and it's 20 high. Okay, so it's 120 meters. Then I have this little triangle here, which is 1 second long by 20 high, right? And then divide that by 2, this is 10. And then this rectangle here, we have 20 high by 4 long, okay? So it's 80 meters. All right, so just to go to find the displacement to E, I add these together, so I've got 100, 220, 230. Oh, sorry, it was only 3 seconds there, wasn't it? That should be, sorry, you're right, that should be only 60. I miscounted. 60. Now it's 210, which is the right answer. Okay, now for part C, the acceleration between F and G, how much would this be out of? It would be out of 1 mark because it's 0. The velocity doesn't change between F and G, okay? It's just the same. All right, and then the total distance traveled. All right, so I'm going to get rid of this 120 here, or I could keep it too. It doesn't really matter, okay? But just for the sake of having the kind of the simplest number of shapes. Okay, so this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 long. All right, and it's 20 high, so this is going to be 200 meters through there. Okay, I still have this triangle that I haven't calculated yet, and it is 20 high by 2 wide. So 20 by 2 is 40, and then divided by 2 is 20. And then I've got this short one that's only 10 high by 1 long, so it's going to be 5. Okay. All right. So but I want total distance. So I mean, not that it matters. There's no negatives here anyway. Okay. I would add all those together, and I'd get 315 meters. Well, if it asks for displacement, then I would want, like, this should have a positive on it, because that's displacement. It should say positive. Yeah. Okay. Yeah, oh, sorry. D was average velocity. Sorry, average velocity, not acceleration. Oh, sorry, yeah, you're right. We skipped D, between A and F. All right, so between A and F, I would need to get the total displacement. So I would just shorten this triangle by 80 by 20 meters? No, by 40 meters. So this would be 160. I'd add those together, okay, and divide by the 10 seconds. Yeah, sorry, I missed that one. Okay, questions on that one? Again, that's just one that makes you practice a lot of things. It's not like one you would get on a test because it takes too long, right? There's just too much kind of, nitpicky work there. All right, that would be more like what you would get on a quiz or a test, would be one like that, okay, because it's got less sections, okay. It's another velocity versus time graph, but maybe let's look at, no, we're not going to do that one. Okay, I'm going to throw you back to a position versus time graph. This is something you have to watch on a test. You got to be able to switch gears, okay, and you got to be able to, you read the question carefully. If it's a position time graph, make sure you're in position time mode, okay, and not velocity time mode. Jake? Next week. Yeah, because tomorrow's class is really short. I'm not going to waste it on a quiz. But Tuesday, yeah. No, it's a normal quiz. Okay. All right, so let's have a look at this one, the position versus time graph this time. So the first part says, what's the average speed over the whole trip? What 2 things do I need to find average speed? Total distance, total time. Well, the total time is 500 seconds. I can read that right off the graph. To get distance, what do I have to do with each section? Add them up. All right, so I'm going to have 500, okay, plus 250, 750. How far do I go here? 0, okay, and then another 750, right? Okay, so 750 plus 750 is 1500, right? Okay, so I got 1500 meters is my total distance divided by 500 seconds. Okay, that should equal 3 meters per second. Okay, and there's no need for a positive on that because it's speed, it's scalar. All right, for part B, what's the average velocity between 300 seconds and 500 seconds? All right, so there's my start and my finish. Average velocity. Okay, and if you look on your formula sheet now that you have it, okay, we see that there's displacement over time, which is final position minus initial position over final time minus initial time, right? That's essentially what we're saying. So the final position is 0, the initial position is 750, right? And that takes 200 seconds. Okay, so 500 minus 300. Okay, well, 750 over 200 should be negative 3.75 meters per second. Sure it is. 0 minus positive 750 is negative 750. Right? Because my final position is 0. I start positive and end up back at 0. That means I have to have gone backwards. I'm moving in a negative direction, even though I don't end up behind where I started. Like originally, I started here for this section. That does mean I end up behind where I started. No, because distance is scalar. It doesn't care which way I went. But this asks for velocity, so I have to use the signage. Okay. All right. Total displacement over the entire trip, 0. Started at 0, ended at 0. Total displacement is 0. Pardon me? That would be a 1-mark question, absolutely. Okay, and for part D, the distance traveled in the first 200 seconds. All right, well, I went from 0 to 750, so it seems like it should be 750. Easy enough. That would probably be a 1-mark question, yeah. All right, everybody, is this starting to make a little bit more sense? Because there's quite a bit of graphing on the unit exam for this, just because graphing is such an important skill in physics. Okay, we've got to be able to use graphs, manipulate graphs, build graphs. Okay, it's a little harder to test that on a unit exam because you're not going to have the Chromebooks, and I'm not going to make you draw one by hand since I've never taught you how to do that. That would be completely unfair. Okay. Okay, this one is again one I'm not going to ask you anymore because it involves you having to draw the tangent line. Okay, so if I want to find the instantaneous velocity at any one of these times, so at let's say 2 seconds, okay, like I've got a number here, but I won't get that number. Okay, I'll give it a try here. So if I draw that tangent line that just touches the curve at time 2 seconds, okay, I find the slope of that line. That'll give me the instantaneous velocity. Well, so I have to estimate some lines here. Maybe I'll use kind of this spot here, 12 and 5, right? So I'll go 12 minus 5 is 7, and that took 3 seconds. So I'm not getting 3, I'm getting something else, right? So every time you draw this, it's a little different, which is again why I don't end up asking it. Okay.
On the test, give us a graph like this with a pre-drawn tangential line that's like more accurate?
No, because then what's the point? All I'm asking is, can you calculate the slope of that line? I'd rather do that in a different kind of question. All right, now is the last one on the worksheet, right? Okay, let's maybe go back and have a look at this one because we didn't go over it. So have a look at 7 right now. Okay, that should take us kind of to the end of today's period. And then we'll talk about acceleration tomorrow. All right, so we got velocity versus time graph. First thing they want is the acceleration between 7 and 9 seconds. All right, so that's for this section here of the graph, okay, between 7 and 9 seconds. So acceleration equals VF minus VI over T. VF is 0, VI is 3, and that takes 2 seconds. So 3 over 2 is negative 1.5 meters per second squared. Okay, so that's how we do part A. Right, it's negative because it's 0 minus 3. So it's negative 3 on the top. All right, questions on part A? No, between 7 and 9 seconds. Just count them here. 1, 2. That's 2 seconds. Yeah? All right. For part B, what's the total displacement between 0 seconds and 7 seconds? All right, so we got to figure out our shapes here. So I'd say triangle there, okay? Maybe rectangle to 7 seconds, okay? And then probably like that, I would say, is probably going to be the shapes I'm going to need. All right, so I've got this little triangle here that's 1 by 1, so its area is 0.5. Then I've got this rectangle that's 1, 2, 3, 4, 5, 6, okay, by 1, so it's 6 meters. And then I've got this triangle here that's 2 high by 2 wide, so it's 2. And then I've got this one that is 2.5 by 2, which is 5. All right, they're all positive because they're all above the x-axis. So if I add them up, I should get 14.5 meters. Oh, wait. Sorry, it's not a half. It's 7. Yeah, sorry, it should be 1, 2, 5. Okay. So no, that's 6. The 6 is right. 1, 2, 6, but this is wrong here. So it's, sorry, 1, 2, 3 by 2. So it's 6. That'll make it work out right. Okay. All right. Questions on that one? Besides, Coder can't count. Okay. Average speed over the whole trip. Well, the only thing we're missing here to get total distance is this last triangle. Right? It won't be that hard as long as I can count this time. Okay, it's 3 high by 2 wide, so 3 times 2 is 6 over 2 is 3. Okay, if I add all of those together and divide by 9, okay, I'll get my average speed over the whole trip. Okay, and then the acceleration between 2 seconds and 4 seconds. All right, so from 2 to 4 is this section here. So my VF will be 3, my VI will be 1. Right, so 3 minus 1 over 2, positive 1 meter per second squared.
Displacement divided by time.
Distance. I just didn't put the positives on there. Right, to calculate distance or displacement is still area under the line. Right, the only difference is if I had negatives, I wouldn't count them as negatives when I'm calculating distance. Right. Okay, so tomorrow we'll start acceleration. No more triangles starting tomorrow.